What is up, calculus students? Back outside. Back outside. Making videos. We're approximating areas under curves. We might draw them to help us see what they are, the rectangles. I don't know. I'm just going to do the problems. We need to also remember how to interpret our answers. So whenever we get to like a free response problem, velocity question, we're going to get on our table, etc., etc. Okay, we want a right Riemann sum and a trapezoidal Riemann sum. I'm going to use the right Riemann sum. We are going to use as many subintervals as can, unless otherwise specified. Key is to do the base, and then a right Riemann sum uses the height on the right. The right Riemann sum uses rectangles. Rectangles areas are base times height. Okay, so my right Riemann sum approximation for this integral from 1 to 13 is going to be a 2 by 9 plus a 2 by 7, a 2 by 4, a 2 by 0. What do you mean 0? Yeah, use 0. You're just going to follow the Riemann sum approach. Key to Riemann sums is we're all going to get the same value for our approximation. You remember, guys, that if it's free response, we don't have to simplify. I'm going to leave my answer like this if I don't have a calculator. Okay? This is fine. No calculator, great. If you have a calculator, might as well type it in. Tried to think about a quicker way to do this using Desmos, and I can't get it yet. If any of you want to investigate, that'd be great. And I get 8. And if I use a trapezoidal Riemann sum, trapezoidal Riemann sums are when we use 1/2 the height, which ends up being my base length or my x distance, and then the sum of my y's. Don't worry about what they look like. Just worry about the formula. Which I will do in a second. So 1/2, 2, 10, and 9. 1/2, 2, 9, and 7. 1/2, 2, 7, and 4. 1/2, 2, 4, and 0. 1/2, 2, 0, and -5. 1/2, 2, -5, -11. Okay. I'll get those values. Since it's a 1/2, 2, I can just sum up the heights. Wait. All right, over or under? Over or under? Well, we were told that the first derivative is negative. If the first derivative is negative, the function is decreasing. The second derivative is negative. If the second derivative is negative, the derivative is decreasing or the function is concave down. If I'm decreasing concave down, if I use a right Riemann sum, I'm going to be using on any base the lowest value for the height over that base. I can tell right away this is under. If I'm using a trapezoidal Riemann sum, I'm using both heights and connecting it with a straight line. I can kind of tell if we are concave down that the trapezoids are ending up underneath as well. Cool. What if I did a midpoint Riemann sum with 3 subintervals? Well, now we would talk about how we would jump over the middle value. We would use the y value on the middle Again, it's a rectangle, but it's your base times your y in the middle, the exact middle, the exact y. So the first one is don't make this mistake, 4 by 9, and then a 4 by 4, then a 4 by -5. You would not be asked if you're over or under midpoints, over or under the actual for midpoints, so don't worry about it. This is approximately. Cool. One thing to remember is that you're accumulating something, and we would get an average of what we're accumulating if we divide it by the interval. So the accumulation of the velocity divided by the interval is the average velocity. It's not the average position. If I accumulated my position over the interval, that'd be my average position. So this is going to be the average F over the interval 1 to 13. We need this 1/12th, and then we need the left Riemann sum. So let's find the left Riemann sum. Two by 10, 2 by 9, 2 by 7, 2 by 4, 2 by 0, 2 by -5. Well, that works out nicely. This is -2, this is 12, this is 30, this is 50, 50/12ths. Approximate f prime of 1. Now, you got to remember the notation would be the slope of f at. Oh, we're going to have to take the derivative, right? Well, the problem is I don't have the function. I don't have f of x. I just have a bunch of points on f of x. So what we'll have to do is approximate a tangent slope with the secant slope. We look at these 2 points. I meant to say 2. The best we can at 1 is honestly just maybe use yeah, I don't know. I wanted to say 2. My bad. So my slope is I decrease 1 over 2 x's. How did I get that? Y2 minus y1 over x2 minus x1, 9 minus 10 over 3 minus 1. Don't make the mistake of doing x's over y's, guys. So many people make that mistake. F prime of 12, the best I'm going to do is to use 10 and 13. -5 to -11, I decrease 6 over the interval 2. 13 minus 11. So decrease 6 over 3 plus 3. Must there be a derivative that equals -7/4? Justify using IVT and MVT. All right. Well, here's the thing. If my slope starts at -1/2, and my slope gets to -3. I can see that my function is continuous and differentiable, which means it has slopes everywhere. There's got to be some x value that will produce a slope of -7/4, which is a slope in between these two values, -1/2 and -3. This is kind of the idea behind the intermediate value theorem. That if f prime of 2 is -1/2 and f prime of 12 is -3, there's got to be some x value that produces the slope -7/4. This is kind of the idea behind the IVT. Now, mean value theorem, this just shows like we'll hit all of our values in between these two values. The mean value theorem is when we know that there has to be a slope that equals a secant slope. It's the idea when I use like the average rate of change formula, I got the slope of a secant, and I said there has to be a tangent slope that equals that secant. Well, here's a trick to these questions, guys. Look at the beginning and the end of your interval. I got 110 and 13 -11. Cool. Well, my slope between those 2 points is down 22 over 13 over 12. Divide the top and bottom by 21. Divide the top and bottom by 3, and I get -7/4. Okay. Since the average rate of change of f equals -7/4 over the interval 1 to 13, there must be
Oh, didn't get you. See you, Mr. Messner.
a derivative that equals that -7/4. I was a little scared. I got a little scared. There must be a derivative that equals that -7/4 on that interval. Cool. Now, here's how we have to always stay on our toes to do this. Well, I don't have f prime. I know this is also equal to this. Sometimes you got to be really ready to use the fundamental theorem of calculus and to use the antiderivative and the displacement. So this would be the change in f. And now we just have to find the value of f of 9 and f of 3. 0, 9, -9. The change in f or the displacement in f. What's the average f prime value? Well, I would love to accumulate f prime from 3 to 9 over my interval. And I realized that, I found that it's just the displacement. The average f prime is the same as the average rate of change of f. Or this answer is -3. Sorry, -3 amps. Oh. What if we want to approximate a Riemann sum and we just have this? Make a table. Oh, we're going from 0 to 2. 9 to the 0 is 1. 9 to the first is 9. 9 squared is 81. I'm using a right Riemann sum with 2 intervals. All right, great. 0 to 1. Base length is 1. Height is 9. 1 to 2, base length is 1, height is 81. Ooh, what if I wanted 4 intervals from 0 to 2? 4 intervals from 0 to 2. What am I to do? I want 4 intervals from 0 to 2. Well, I would have to divide this interval into 4 equal parts. Each of the parts would be a half, which means I need 9 to the 1 half, and I need 9 to the 3 halves. That's the square root of 9 cubed, which is 27. And now, my approximation will be 1 half times 3 a half times 9, a half of 27, and a half of 81. And we got the 8, 118, 121. Whatever that is. 90. Is that right? Three, 9, 27, 81. So 60. 12. Given that this function is increasing, are my right Riemann sum approximations over or under? Well, if we have an increasing function and I'm using the y coordinate on the right, if I'm using the y coordinate on the right for a base, I'm using the highest y value over the interval, which means we're definitely going to be over. Okay. Let's do a table. Trapezoidal Riemann sum is going to be 1 half width of 1, heights of 1, 0, and 1. I got 1 half width of 1, height of 1 and 4. I got a 1 half width of 1, height of 4 and 9. And I got a 1 half width of 1, heights of 9 and 16. Midpoint, I got 0 to 2 using 1. I got 2 to 4 using 9. Use the y coordinate in the middle. There's a little secret to trapezoidal Riemann sum. If you have a consistent base, you have 1 half your consistent base. You have your first plus your last that occur once, and then you have the numbers in the middle occurring twice. If you don't understand that, don't worry. All right, well, I know the first derivative is 2x. I know from 0 to 4. I mean, I honestly don't need to do this sign analysis. You know what x squared looks like. But you know from 0 to 4, that's your first derivative is positive. At 0, it's 0, it's positive. So that means f is increasing. I know that the second derivative is 2. That means the second derivative is always positive. Means the first derivative is increasing to minus per x per x. That means the original function is going to be concave up. Okay. Is the trapezoidal sum over or under? Well, if we have an increasing concave up function and we're using a base length that's an x distance and both y coordinates that are over the base, we can kind of see because of the curvature that the trapezoidal Riemann sum is over the actual. Find the actual area. Well, we know that the accumulation of f equals super f of 4 minus super f of 0. Any level works for this. We started with accumulation of velocity, changing of positions. I need super f. Super f is 1/3 x cubed plus c. Super f of 4 is 4 cubed. 1664, right? 64 thirds. And then super f of 0 is just c. Those c's will go away. That's how I get 64 thirds when I subtract. Now let's look. Let's just double check. I got my trapezoidal Riemann sum was 22. What's 64 thirds? And I know that's more. 64 thirds is 21.333. I got a very good approximation. I know that it's over the actual. This is like why we do this. Finding the exact and finding the approximation. It's cool to see that. This is a good challenge. I need super f. I need super f. What is the antiderivative of 9 to the x? Well, I'm sure you don't remember, but it's 9 to the x divided by the natural log of 9. We have to remember the derivative of 9 to the x. Since the derivative of 9 to the x is 9 to the x times the natural log of 9, when I take the antiderivative, I start with 9 to the x, knowing that I'll have a log 9 when I take the derivative. I know I need to divide by log 9, or I need a 1 over log 9. So, super f of 2 is 81 over log 9. Let's see. Super f of 0 is 1 over log 9 plus c. That means this super f of 2 minus super f of 0 is 81 over log 9 minus 1 over log 9. So that's the actual area. I found approximations where it's an increasing function. So I know that this 60 is over. Let's see what the actual is. We also should have double checked doing the integral from 0 to 4 of x squared. Just to see yeah, your calculator gets this completely differently from how we got it. Let's see what we got. Well, let's probably do this backwards. Let's integrate from 0 to 2, 9 to the x. 36.409. I'm saying that's 81 over log 9 minus 1 over log 9. Look at that. And 36.4 is less than the 60, which is our over approximation. Much less than. That's fine. All right, we're going to finish up with 2 free response questions, 2 velocity questions where I'm given a table of velocities. So here we go. All right. P prime, P double prime, position, velocity, acceleration, which is the derivative of velocity, meters, meters per second squared. If I integrate velocity, I will be getting a displacement of position in meters, or the change in position in meters. How much my position changed in meters. If I take the derivative of velocity, I'll get an acceleration. Okay, left Riemann sum. I got base of 2, height of -2. I got base of 1, height of 0. I got base of 2, height of 6, height of 3, base of 3, height of 7. So that's 23. Right Riemann sum. I got a 2 by 0, 1 by 3, a 2 by 7, and a 3 by 12. 53. Trapezoidal Riemann sum. I'm not going to do the calculation. I'll have a 1/2 base length of 2, y on the left, y on the right, plus 1/2 base length of 1, y on the left, y on the right, plus 1/2 base of 2, y on the left, y on the right, plus 1/2 base of 3, y on the left, y on the right. Given my velocity is derivatives positive and second derivatives positive, my velocity is increasing concave up. If I use a left Riemann sum, the left Riemann sum for increasing functions will use the lowest value. So the left Riemann sum's under. The right Riemann sum is going to be over. Because of my concavity, if you have some increasing concave up function, your trapezoids will be over. And you need to draw the approximation, or draw to see, to be confident in your answers. What's an approximation for A of 4? It's the same as V prime of 4. I'm going to use the slope of V between 3 and 5. I have 7 minus 3 over 5 minus 3. So that is an increase of 4 meters per second over the course of 2 seconds. So that's 2 meters per second squared. Was arranged possibilities for the position of the person at t equals 8. The position is located, person is located in a position of 3 at t equals 0. You got to remember that your position I didn't want to do this. I honestly, I really did not. You got to remember that your position of 0 being 3 and your position at 8, you needed to use the position at time 0 and you need to add the accumulation of the derivative. You needed that p of 8 equals p of 0. Many of you, I think, remember this from the stuff that we did last unit with rate in, rate out. So remembering that the low end will be our left Riemann sum. So 3 plus 23 using our left Riemann sum. And then 3 plus 23, 3 plus 53 is 56. Like 3 plus 23 is 26. And that's using our right Riemann sum. So this is our position, a range of positions that we could have had. Okay, using my right Riemann sum, if I take this number and divide it by 8, I get my average velocity. What is the units for velocity? Meters per second. But it's like, well, didn't I accumulate velocity, which gives us change of position? Isn't that meters? Yes, but then you're dividing it over the interval of seconds. So you accumulate this and you get 53 meters, but you're dividing it by 8 seconds. That's how we get meters per second. Ooh, what if it's the absolute value of V? Since it's a right Riemann sum, I should be using left Riemann sum. If it was a left Riemann sum, we'd have a different value. If it was a left Riemann sum, we wouldn't have this -4. If it was a left Riemann sum, it'd be a +4. It's so annoying when my computer slows down because I'm doing this. Oh my gosh. Why are you so slow? It's so, I gotta like close this out. Oh my gosh. So turn it to a +4 for the first interval. So 4 plus 6 plus 21 is 31. It'd be meters. What would that represent? That'd be the distance traveled. Approximation. What would be a value of the integral from 0 to 8 of a? It'd be v of 8 minus v of 0. What is v of 8? It's 12. V of 0, 2. 10. What is it? Meters per second. It is the change in my velocity. This is the fundamental theorem of calculus. An accumulation is equal to the change in the antiderivative. What if I do this? Well, I get v of 5 minus v of 2 divided by 3. I'm going to get an average rate of change of velocity, which is an average acceleration. This is going to be meters per second, velocity minus velocity. But over the course of 3 seconds, that's why it's an average acceleration. V of 5 is 7. V of 2 is 0, so it's 7. V of 2 is 0. Okay, so 7 over 3. 7/3 meters per second squared, average acceleration. Okay. Ben's acceleration. Best thing to do with Ben's acceleration is to approximate the derivative of the velocity at 5. I'm going to use my velocities from 0 to 10, which I get 2.3 minus 2 over 10 minus 0. And I'm going to get 0.3 over 10, which is 0.03 meters per second squared. And then my derivative at 50, I'm going to use 40 and 60. I'll have 4.6 minus 2.5 over 20, 2.1 over 20, whatever that is. 21/20 meters per second squared. Is there a time when Ben's acceleration must be 13 over 300? Well, starting from point, what's 13 over 300? Oh, starting from point 0.03 and going to this value, we know that our slopes must pass through that, provided my function is continuous and differentiable. That's kind of like a mean intermediate value theorem approach. Or you use the mean value theorem. There has to be a derivative of velocity at some time that equals, let's look at the beginning to our end, 4.6 minus 2.0 over 60. Look at that. Yes. The average rate of change of V from 0 to 60 is is 13 over 300. Therefore, since the function is differentiable, there has to be a acceleration that equals that value. Approximate Ben's average position using a trapezoidal Riemann sum with subintervals indicated by the data. How do I find an average position? Well, I need to accumulate what I'm trying to find the average of, add it up. That's the position. And divide it by the second. So when I accumulate P, I have super P. If this is in meters, this is meters per second, and this is meters per second squared. This will be in meter seconds, just multiply by seconds. But when I take our meter seconds and divide it by seconds, I'll get meters, which is why I get an average position. So this is equal to our meter seconds, but I'm going to divide it by seconds and get meters. I get an average position. Now my position is apparently B of t, so I should be using B of t. And I'm going to move the 1 over 60 out, and I'm going to use a trapezoidal Riemann sum. So I'll have 1 half 10, 100 and 136. I have a 1 half 30, a 136 and 9. And then I have a 1 half 20, 9 and 49. Whatever that equals, divided by 60, I get an average position in meters. Approximate this integral using a right Riemann sum with subintervals indicated by the data using correct units. What does your value mean? So if I accumulate my velocity, I'll have a change in position. I'll get meters. I'm not dividing it by anything, so it's not a meters per second. It's just going to be meters. So I'm going to use a right Riemann sum. That's going to be a 10 by 2.3 plus a 30 by 2.5 plus a 20 by 4.6, whatever that value is. This is going to be meters. And that is going to be the change in my position, an approximate change in position. Compare this approximation to the actual value of the integral from 0 to 60 of v. What do you mean the actual value? Well, guys, I have the change in my position, right? This equals my position at time 60 minus my position at 0. The accumulation of your velocity equals your change of your position. My position at 60 is 49. My position at 0 is 100. I lose 51 meters. This is a positive value. This is a negative value. Whoa. Completely different. Shows you like having a velocity at a point in time doesn't tell you much. Just because these velocities here are all positive, must there be a time when the velocity equals 0? Yes, my velocity has to be negative. How do I know that? Because look at this situation. My meters decrease. I go from 136 to 9. My position decreases. Therefore, its derivative must be negative for some points. So, yes, my position increases from 100 to 136. And then my position decreases from 136 to 9. If your position increases, then decreases. Your derivative must change from positive to negative. There will be a time when my position will be stagnant at some value, so that my position changes from increasing to decreasing, my velocity will be positive and then 0 and then negative. Yes. Your position increases, then decreases. Your function is differentiable. There has to be a 0. All right. Here's a trick. My position at time 60 plus the accumulation of my velocity from 60 to 120 is going to give me my approximation. Guess what? I have my position at time 60. This is a really tricky question because nobody thinks to look back. I need 49 plus my left Riemann sum, which is a 10. Everything's a 10, so I'm just going to use 10 over and over. So 3.5, 2, 1, -4, -3. Cool. But I add that to 49. What's your average velocity over the second minute using a midpoint Riemann sum? Oh, cool. Well, I want to accumulate my velocity to get my meters displaced on average over the time interval of seconds. So I'm going to use my midpoint Riemann sum, which is a 20 by 2 plus a 20 by -4 plus a 20 by 1 over 60, whatever that is. This will be meters displaced. This is seconds, meters per second. And find the value, use your calculator on that. Okay. All right. I didn't want to do that, but I did it. The key is to understand how to calculate the Riemann sums, but to not forget anything else we've done over the course of this unit. Okay. All right. Peace.